Hello, my name is David Forman. I'm an undergraduate at Hillsdale College, and I've worked with Dr. Tracianne Neilsen on underwater acoustics. And so if we're doing passive seabed characterization, we want to be listening to a pulse waveform from a sus charge, a 1-second waveform. We want to have a convolutional neural network that can predict from that waveform what kind of seabed impacted its propagation. Maybe it was a muddy seabed, maybe it was a sandy seabed. So you've got different shapes of propagated pulses, and you've got your sus charge and you've got your receiving hydrophone, and they'll sound different. We want a classifier to hear that and predict a class of seabed type that is similar to what the propagated pulse would have experienced. This is a different approach than looking at individual parameters, which a lot of work is done in individual parameters of different sediment layers, sound speed, attenuation, density, many different individual parameters for a given seabed, and that's how you might characterize a seabed. But this overall acoustic type emphasizes the effect in the water column rather than the individual sediment layers. It avoids overfitting in case it's not possible to distinguish two different sediment structures that have the same overall effect. It also avoids non-physical combinations of individual parameters that you might get with an individual parameter model, rather than giving back a class that is at least physical, if not a very similar class to the true seabed that we're looking for. And so if you've got your pulse that's incoming, you've got your classifier. If the pulse that's incoming is from a seabed that isn't in your set of seabeds that your classifier has been trained for, then we want the classifier to give a similar result to match the waveform and the seabed that produced this waveform to a similar seabed. So for example, if this pulse is truly mud over sand, is the seabed environment, and we only have sand and muddy and gravel and different types, we want the classifier to at least assign it to either the mud or the sandy rather than the gravel. We want a similar seabed chosen from our catalog of seabed types. So that's what we want our classifier to be doing. And to do that, we need a measure of similarity. How do we measure similarity? Is the mud over sand more similar to the muddy, or is it more similar to the sandy? It's hard to say without developing some sort of measure. So that's where we have this transmission loss measure. We see a shallow ocean of 80 meters, 2 to 12 kilometers in distance, different transmission loss amounts, and you've got your hydrophone depth of 79.5 meters. So what we're interested in is, at this depth, what's the transmission loss over distance? And also it's different at different frequencies. So we've got these two different dimensions of information, and we can concatenate, range and frequency and get an overall transmission loss vector. For 13 different frequencies, you've got a lot of different range numbers, and you can get this overall characteristic vector of the transmission loss of a seabed, and you can compare them against each other. You can find the proportionality between two different characteristic vectors. And so we can just look by eye, the two vectors on top look not as similar as the two vectors on the bottom of this chart. And the Pearson correlation reflects that. 0.35 correlation between the two on top and 0.75 between the two on bottom. So we see that a Pearson correlation measure of proportionality from basically 0, which is no proportionality, or -1, which is anti-correlation, but 0 to 1, we can get meaningful numbers here. 0.35 shows a little bit of similarity. 0.75 is more similar. And so this will be our measure of seabed acoustic similarity. This is what we will judge our model by. We see that it works for 4 exemplary seabeds. These are taken from Van Komen et al. 2020. You've got deep mud, you've got sand, you've got mud over sand, and you see if we make a grid that deep mud is 1.0, similar to itself, of course, similar to mud over sand, not similar to sand. In parallel, sand is not similar to deep mud and is perfectly correlated with itself. If we find a lot more geoacoustic profiles than just these 30 different profiles, we can make a large matrix to compare these profiles to each other and find a set of seabeds for our catalog. We want these seabeds to be acoustically distinct, ones that we can distinguish, not distinguishing 14 types of sand. We want types that are different from each other. And so we order this matrix according to dissimilarity, and we get a group that's diverse acoustically up here. You see those first 4 seed profiles that we chose, and then dissimilar seabeds. So these make up our representative seabed types. And then our testing seabeds are somewhat similar to these seabeds, but none of them perfectly the same as the representative seabeds. And so those will be our testing seabeds. And you can see how similar they are, some of them very similar to each other, but how similar they are to the representative seabeds. So we've chosen our catalog of seabed types and our testing seabeds for these unknown poles. We're going to say this is similar to seabed type 1, seabed type 13. We simulate waveforms, 23 different sound speed profiles of the water, 40 different source receiver ranges. We have 920 waveforms per seabed simulated according to the ORCA model. And this is what we're going to be training our model to distinguish. So our model is a convolutional neural network model in 1 dimension based on Van Komen et al. 2020. It's the same kind of model, similar, some specification changes. And overall, it has about 100% accuracy in distinguishing our distinct seabed types. These 13 representative seabeds, we can very well distinguish from each other with 5-fold cross-validation of our classifier. And so we know that our classifier can learn something. It can distinguish these 13 seabed types. So that's sort of traditional classification problem. Look at these 13 types, see whether we can distinguish them from each other. Now is our new research, is looking at a new type, a testing seabed that we haven't seen before, and how well does our classifier choose a matching seabed? So we have these results. We have these testing seabeds and all of these waveforms, and their waveforms are assigned, oh, I think that's similar to type seabed R1, type R13, our catalog of representative seabeds. And so we have these testing seabeds, and this is basically a confusion matrix in machine learning where you've got T14 is often assigned to seabed R3, sometimes, or even more so, to seabed R9. You've got sort of our fractional assignments to each of the different types for each row. And so each row should add up to 1.0. And for example, in the final row, seabed T30, it sums up to 1.0 because everything is assigned to seabed R10. So we'd very much hope that seabed R10, representative type 10, is similar to seabed T30. And we see that that's the case. If we show our representative seabeds and testing seabeds with the Pearson correlation between them, we see that for seabed type T30, R10 is the most similar seabed. And so our classifier must know something. It's assigning seabed type T30, the waveforms from that, it's saying, oh, you sound very similar to my representative type 10. But it's not as nice as that for our first, it's not as nice as that for our first row. Seabed type T14, its waveforms are assigned to R9 and R3. R9 is the most similar seabed. R3 is not. So you've got half of the results are very good up here, but half of them are not. And we could go through individually and see, nice things, not so nice things. We need to look at this in a more overall view. And this is where we get our cumulative distribution function. A lot of lines. What does this mean? Well, if we had a random classifier, what would happen? A random classifier would look at a new waveform and wouldn't have a clue and would just assign it to one of the 13 types. So on this cumulative distribution function, the first seabed type, it would assign randomly a 13th of the seabeds to, and then the second type, it would add another 13th to, and so cumulatively, in the end, you'd say, well, we've got a 100% placement within one of the 13 most similar seabed types, but you've just got a random classifier and it's only got 1/13th placement within the most similar seabed type. We'd hope that our main results are better than this. If we track a single seabed, maybe it will make more sense. So seabed type T26 here in the green dashed line, in the high 70%, its waveforms are matched to the most similar seabed within the representative seabed set for it. And then by the top 3 most similar seabeds within the representative set for it, it's at about 100% placement within one of those top 3 as you climb the cumulative distribution function. Or for type T29, you start out and none of its waveforms are assigned to the most similar seabed within the representative set. But a lot of its waveforms are assigned to the second most similar seabed within the representative set. And so you climb to 100% by step 2, and then you're at 100% the rest of the way. And so overall, if we take a median of these 17 different seabed results, we find that we are doing better than average. 65% on median of the waveforms are given the best choice seabed within the representative set as measured by the Pearson correlation measure. Also, you've got, if you climb up here and say, well, maybe we care about placing a new waveform within one of the top 3 most similar representative seabeds, we're at 95% accuracy for that. And so we're seeing that our convolutional neural network is doing better than random. It is seeing a new seabed type and matching it to a similar seabed type, maybe not the most similar seabed type, but a similar seabed type within its representative set. And so this median dark line shows that we do very well, at least within the top 3 most similar seabeds, we can match a new waveform. And so this shows that our deep learning model understands some physics. It's matching the transmission loss measure of similarity to some degree. Secondly, we could also say, well, the transmission loss measure of similarity is working as a measure of seabed similarity. And we could just see that intuitively where it showed that deep mud seabed is similar to a mud over sand seabed. And it's not very similar to sandy. So this transmission loss measure can measure the overall similarity between seabeds. And finally, this measure of similarity helps us choose a catalog of distinct seabed classes that are acoustically distinct. And so these are our overall conclusions. We've extended the idea of classification, where we have these 13 classes and can we distinguish them from each other, these 13 different types of seabeds, to, well, let's take a new seabed type and see whether we can match it to a similar seabed type within our catalog. So this is our extension of the classification approach to characterizing seabeds passively, just listening in on them with a deep learning algorithm. Thank you, Dr. Neilsen. Thank you to Dr. Van Huel, Dr. Colton of BYU RU program, and to the National Science Foundation.